All right. Well, hopefully on practice one, everybody found their t-score to be 1.796. And if you didn't, just let me know if you came up with something different. All right. So to calculate our confidence intervals by hand, again, these are going to be practically the exact same steps with just a few little substitutions. So again, we definitely need to know the sample mean. That's going to be the one and most important thing that's necessary. So in this case, either the sample standard deviation is given to us or we can find it, and we know how to do that using like our 1 var stats, of course. And then we want to take and use our central limit theorem to write out what the standard deviation is going to be, dividing by the square root of n. And then finally, we want to find our t-value, either using the table, inverse t, or the Google Sheets, whichever one, that corresponds to the given alpha level. So again, writing these out, the only difference between this and 7.1 is instead of using the zebra, we're using the tiger, and we're using the sample standard deviation instead of the sigma. The next statement, again, is expanded form. This is identical to what we had in 7.1 with, again, those minor substitutions. The part here, again, is still called the margin of error. And then again, we can streamline this and write it in this nice margin of error form, just like we had before. All right, so let's dive in and take a look at how to find a confidence interval. So let's look at example 2 here. So a potato chip company wants to evaluate the accuracy of its potato chip bag filling machine. Bags are labeled as containing 8 ounces of potato chips. A simple random sample of 12 bags had a mean weight of 8.12 ounces with a sample standard deviation of 0.1. Construct a 99% confidence interval for the population mean weight of bags of potato chips. All right, so again, let's write down everything that we know. So in this case, we've got our sample size was 12, so we've got our n is 12. Our sample mean is the 8.12 ounces, so we've got our x bar, sorry, 8.12. Our sample standard deviation is 0.1, and we want to construct a 99% confidence interval, so our alpha is going to be 0.01, which means in terms of trying to find our t-score, we want to think of this as 0.005. And so we still need our t-score to go along with this. Oh, and then our degrees of freedom, of course, is going to be 11. All right, so let's first start off and find our t-score before we do anything. So we're going to need our inverse t, our 0.005, comma, our degrees of freedom, which is 11. All right, so second vars, inverse t, 0.005, comma 11. So we end up with negative 3.11 as our t-score. So I'm just going to write the positive version, but again, remember we're going to get the plus or minus of each of those. So 3.11. And so now we've got everything we need to go ahead and set this up. So just like before, we want to calculate our upper bound. So we're going to take our sample mean plus our t-score times our s, all divided by the square root of n. So we've got 8.12 plus 3.11 times our 0.1 divided by the square root of 12. And so let's throw that in the calculator real quick. So 8.1, oops, I think it's just 8.1, let's see. 12, sorry. 8.12 plus 3.11 times 0.1 divided by square root of 12. So that takes us out to 8.21 as our upper bound. And then our lower bound is going to be, again, same thing but with a minus. So t times s divided by square root of n. So 8.12 minus 3.11 times 0.1, all divided by square root of 12. And so again, if we go back to the calculator, we can just hit second enter, change this plus to a minus. And so we end up with 8.03. So again, writing this out in interval form, then we'd expect with 99% accuracy that the sample or the population mean should live somewhere between 8.03 and 8.21. So in this case, we are 99% confident that the population mean is between 8.03 and 8.21. All right, and so if you remember originally, and not that this question is being asked here, but it may be eventually, that the company claims that every bag of chips contains 8 ounces of potato chips. And so does it seem reasonable that 8 ounces is actually the population mean? Well, according to this, it's actually a little bit lower than our confidence interval that we have. I mean, it's good for us because it looks like we're getting more than what the company actually claims to be getting. It would be bad if you were running the company because if you're actually given even just a little bit more, that's going to cut into your profits and things like that. So in this case, I'd say that their machine's not quite accurate enough. It's actually putting in a few more potato chips than it should be if the population mean doesn't actually live within that interval that we're looking on. So that's eventually where we want to go with these types of problems to be able to make estimations and conclusions about things based on this confidence interval that we're finding. All right. So one other note that I want to make is notice with I guess another big difference between what we're doing right now and what we did with 7.1 is remember with 7.1, since nothing was based off degrees of freedom, if we knew we had a confidence interval, then we knew that our z-score would always be 1.96. But here, we could still have a 95% confidence interval with 10 different problems, but if they all had different n values, we'd still have to go in each and every time and calculate inverse t to figure out our t or tiger score for all of these guys. So just kind of keep that in mind. We can't reuse scores unless the n would happen to be exactly the same. So more than likely, every single problem, we're going to have to usually go in and calculate a new tiger score for these, where we don't in 7.1. All right, so everybody, let's try a couple of these practice problems. Make sure we're on the right track. So we've got practice 2, practice 3, practice 4, practice 5. And then let's come back and talk about practice 6 together. So go ahead, work on those. If you have any questions or anything, just let me know.